Okay, thank you all for coming. I'm basically the entire, that's fine. I think people can hear me. I think the committee is here, and so we can get started. So Sarath Sreedharan will be defending his PhD dissertation titled Foundations of Human-Aware Explanations for Sequential Decision-Making Problems. His thesis committee consists of David Smith, formerly of NASA, sitting here, Bean Kim of Google Brain, who is on Zoom, Sreedharan, Srivastava, and Tony Chan, who are both here in person, and myself. And then subject to his successful defense today, Sarath plans to join as a faculty member of computer science at Colorado State University starting this fall. Before we get started with the formal proceedings, I would like to say just a few words about Sarath, which is sort of the things that we do in our group. So Sarath joined the ASU PhD program in 2016 after having successfully completed a master's thesis here that actually received the Department Outstanding Master's Thesis Award. He did, as part of his MS, do a LinkedIn internship, but apparently decided money is overrated. So he decided to join PhD instead. In the 6 years that he has been in the PhD program, Sarath did highly impactful work, at least as far as I can tell, on explainable human-AI interaction. He wrote scats of papers that appeared in almost every top conference in AI, including AAAI, HCAI, ICAPS, ICLAIR, ICML, and the AI Journal. And these papers have apparently been read too, because they have garnered an astounding 1,300 plus citations. I guess a number that would be the envy of many people, even going up for tenure in many universities. And again, a number that he got without being a co-author of either the TensorFlow or the PyTorch paper. So he co-delivered tutorials, delivered summer school lectures, and was the lead author of a book we wrote on explainable human-AI interaction that came out in the beginning of this year. And Sarath also has been on the program committees of pretty much all the conferences, and he is, even received one of an outstanding reviewer award at AAAI 2020, one of just 12 of the people. And so I believe he also got like a free registration for NeurIPS for being in the top K% of the reviewers. So Sarath is an extraordinarily disciplined and hardworking researcher. He is often involved in multiple projects and mentoring roles in my lab. Except during the dark days of the pandemic, he was pretty much a fixture in the lab most days, including the weekends. He is an excellent sounding board for ideas for pretty much anyone in the lab. A non-trivial catalyst for me to show up to the lab has been to have impromptu lab wall-side chats with him and others in the lab. Not surprisingly, he's been a mentor and almost a second advisor to many other students in the lab, with whom he's generous with his time and scrupulous in sharing and giving credit. His preternatural research maturity is so much beyond what one expects in a grad student that recently, when one of the papers he was involved in got a best paper award at a workshop, the workshop organizers asked us if they can give the prize to just the student author, assuming that neither Sarath nor I were students. So despite his passion for his research, Sarath is a gentle soul whose biggest worry tends to be that he might have inadvertently offended someone. So much so that sorry is the nickname he's known by all of us in the lab. I know some of you are wondering how the heck did he become Rav's student if he's that worried about offending people. But anyway, the sorry is certainly not an indication of any lack of confidence he has in his work. He can defend his ideas quite vigorously. I hope he'll do that today. I've been fortunate to have worked with quite a few amazing PhD students over the years. And the thing I remember about Sarath is that he's a true scholar in sort of the best sense of the word. Truth be told, he was really a poorly paid senior postdoc, junior colleague to me for quite some time. A colleague probably with an annoying tendency to say sorry a little too frequently. We will certainly miss him if the committee decides to pass him today. So that's all I have to say. Thank you, Sarath. Go ahead and do it.
I'll just start. Okay. Okay. Sorry about that. I'll just pick it up from here. I don't think it's anything to do with the mouse, but yeah. Okay. So the basic setting consists of a robot using its model to come up with a plan, which is actually in this case, at least in the room, it's slightly cut off, but it's coming with a plan called PyStar MR. And the human has its own model of the task, which is called MRH. And they are trying to come up with their plan based on, or at least they form an expectation on what the robot should do. And this plan is PyStar MR. At least this is the plan that the human thinks the robot should be doing. So within this human-aware planning setting, one of the most basic problems that can come up is what happens when the plan that's chosen by the robot is different from what the human was expecting. So we call this as the problem of inexplicability. And if you are to come up with systems that can effectively operate in this setting, it has to in some way address this mismatch in expectations. So broadly speaking, there are two strategies for addressing this issue. The first one is what's usually referred to as explicable planning. So in this setting, what the robot will do is, okay, let's not worry about what the right course of action is based on the robot's model, but instead what the robot could try to do is come up with a plan that's close to what the human is expecting. So this is called explicable planning. But the strategy that I'll be focusing on in this talk and in my dissertation is what's called as explanation. So what the basic strategy here is, the robot is going to choose the plan it thinks is the right one to do based on its model, and then try to explain its decision to the human. So this is basically it's trying to explain why this is maybe optimal or bad, depending on the setting. It's trying to explain why this is the right decision to do. And this is the basic view of explanation that I'll follow within my dissertation. It's a fact that explanation is fundamentally a process of reconciling these differences in expectation. So it's trying to get the human to see why this might be the right course of action for this setting. And another way of also looking at this explanation process is to think of it as a dialogue. And usually you can think of most of the explanation I'll be discussing. In fact, all of the explanations I will be discussing as an answer to a why question. Basically, specifically, two kinds of why questions. One is a question of the form, why was this plan PyStar MR selected, which was the robot's plan? Or what's usually called as an explicit contrastive question, where the human might ask, why was this plan selected over an alternative or a foil that they were expecting? Okay. So to me, or at least in the view of the dissertation, explanation in some sense involves addressing asymmetries along these three dimensions. The first two dimensions correspond to sources of possible mismatch between the expectation. That is, there could be a mismatch between the human's knowledge of the task and the robot's knowledge of the task. And there could also be a mismatch between humans' inferential capabilities and the system's inferential capabilities it's using to come up with the decision. And these mismatch would cause the human and the system to disagree on what the right decision to do is. The third dimension is about vocabulary mismatch. This is basically about the fact that the human and the system might be making sense of the world in very different terms. And if it has to effectively communicate why it chose to do it, it has to do it in terms that the human would understand. So this is also a dimension that has to be addressed by effective explanation generation algorithms. So this is going to be the basic outline of the talk today. So I'm going to, the main focus of the talk is going to be about the work I've done along these three dimensions. So we'll start by talking about the work I've done in asymmetry, like addressing asymmetry in the first dimension, which is the difference in knowledge, then how do we explain decisions to human when there is asymmetry in differential capability? And finally, addressing scenarios where there are vocabulary mismatch. Then I'll quickly go over some of the other works that are related works that I've done with respect to explanation. Specifically, I'll talk about coming up with interpretable behavior, where especially I'll focus on algorithms that try to balance explanation, which is like communication, with choosing behaviors that are easier to explain. So these are called balancing planning algorithms. So we quickly look at that. Then we'll look at specifically one work that I did to summarize policies, especially like in stochastic setting where policies could be extremely large because of it has to account for different contingencies. We'll look at how one could leverage techniques from classical planning to create summaries. And I would like to then take a quick look at how we can use this lens of human-aware explanation, and in particular these three dimensions, as a way of understanding the current landscape of explainable planning works. So I won't spend too much time in this. Most of the details are in the presentation, but I'll give you like a quick summary of the kind of works that have been done to address the different dimensions. That goes beyond just the works that I've done. And finally, I would like to end the defense by going over some of the next steps where this work could lead to. Okay, so this is again just like a summary of the kind of the papers that this dissertation covers and some of the talks covers, and the various venues where they've been published. Okay, so the first part is about addressing asymmetry in knowledge. To start with, when I'm talking about asymmetry in knowledge, what I basically mean is going back to our human-aware planning setting, the basic one we talked about. I said there's a model that the robot has of the task, which it's using to come up with a decision. And then there is the model that the human thinks is the model of the task, which the human is using to come up with their expectation on what should be done. And a knowledge asymmetry or model asymmetry exists when these models don't match in terms of the character. And what that means is, even in these settings, even if the robot was using an optimal planning algorithm, the plans it might come up with might look invalid or suboptimal to the human. So this would cause the human to ask, like, why was this plan being selected? So obviously, since the problem is given the fact the problem arises from the fact that the models don't match, the solution seems simple, right? Yeah, why don't we just give the robots model so they can correctly evaluate the plan in question? Unfortunately, even in the simplest case, this could be an extremely demanding process towards the human. So just to give a simple example, just consider a robot that's trying to, that's being tasked with creating a stack of 3 blocks. But the robot is now kind of doing this weird circuitous thing where it's actually picking, like destroying this already partially formed 2-block stack and then forming this 3-block stack. And it might look confusing to anybody who's looking at it. And if you were to ask why it did it, just imagine the robot just dumping this entire trace, right? It could contain so many information that the human did not know before. This is completely irrelevant to the problem at hand. All we were interested in knowing was why did it unstack those already formed stack instead of just picking it up and putting it here, right? But now we have to go through this entire huge, what more or less amounts to the entire description of the robot model. So this, I would imagine hopefully you would agree that this is unnecessary. So what we did was we looked at these kinds of explanation problems within this framework called model differentiation, where our objective was, how do we calculate the minimal amount of information that the robot has to give to the human? So once they receive it and they have an updated mental model of what the task is, they can correctly evaluate the plan. And by correctly evaluating the plan in question, I mean the plan will be, the updated model, the plan will be valid and updated. So this is called as model reconciliation explanation, especially specifically this refers to a kind of explanation within this framework called minimally complete explanation. And the standard way of generating such explanation, and also in some way to visualize this explanation process, is to think about you have the human's mental model at one end, you have the robot's mental model at the other, and you are trying to give the minimal amount of information. So you can think of it as a search space over possible models, and you're trying to provide update the human's model minimally, so you get to a model where the objectives are met, which is basically the plan is going to be optimal. So this takes this form of this search over the space of mental models, possible models. So in this particular example I discussed, seems to be a delay. The explanation was simple as saying, okay, the robot can only pick up light blocks, and the purple block is not a light. So if you look back at the video, it couldn't pick up the purple block because it was not a light block, and it can only pick up light blocks. So that was the explanation. We don't have to go through this entire model to figure that, just to understand that. Right? So you can just give the minimal information there. So this is the model reconciliation search, and this corresponds to the minimally complete explanation. Within this framework, we've also looked at some other forms of explanation. One of them was, I won't go into the details of each and every one of explanation type we covered, but one specific one that might be worth mentioning is what we call minimally monotonic explanation. And this is more geared towards longitudinal interaction, wherein these explanations guarantee that no matter what future information the human might receive, the validity of the previously explained plans will not be changed. So it just ensures that regardless of additional information, old explanation stays correct. So in terms of evaluation, one of the first things I did was evaluate the effectiveness of the algorithms itself on some benchmark domains, and these are from this set of benchmark called IPC benchmarks, and it's very popular within automated planning community. And you will see that I've done this kind of evaluation for most of my work over different kinds of benchmarks. So here you can just see especially the time taken for different kinds of explanation. We've also looked at different heuristic ways of generating it, ways of approximating it. But maybe a little more interesting one would be the kind of user studies we've done to validate the explanation. And specifically, one of the studies we did was one where participants were allowed to actually view different plans or different maps, and they were exposed to different kinds of explanations. Some of those explanations correspond to various types of model reconciliation explanation, and we were interested in knowing whether being exposed to these explanations allowed them to better understand the properties of the plan in question. So whether they are able to predict whether the plan is valid, optimal, so on, after seeing the explanation. So the results were pretty much in line with our hypothesis. And in fact, we did see that when we were giving the minimal explanation as opposed to just dumping the entire model to the human, more people seem to be able to better validate the properties of the plan in question. So that's about the basic framework. And what we will do to the rest of this section is we are going to revisit this idea of generating minimal explanation, but while relaxing different conditions that we made here. And I'll go through how we can still generate these kind of minimal explanation in those settings. But before we take a look at those, I just wanted to quickly discuss one of the newer results, which was basically what is the complexity, the computational complexity of generating these kind of minimal explanations in the most basic setting. That is setting where the planning problems are deterministic. We know the human's mental model and so on. There's Strips model and things like that. I don't want to spend too much time in this, but just to give a quick idea. So what we found out was the complexity of generating an explanation of size thing. We found it to be sigma to be complete. So just to give you guys what that really means. So sigma to be complexity is usually placed between NP and P states. And one of the interesting side effects of this proof has been the fact that we now have a quantified Boolean formula compilation for generating such explanations. So these could be future candidates for generating minimal explanations. So we don't really have to do this model space search, and instead could use QTF solvers. In fact, it's a restricted class of QTF. True QTF is in P space, but we can still use not like effective QTF solvers to come up with these kind of solutions, these kind of explanations. So I won't go through the actual compilation and things like that, but come to one of the first variations on model localization. And here, by variation, we are going to take one of the fundamental assumptions made by this framework and try to see how we can relax. So one of the assumptions that we had made is we were talking about how we can figure out what explanation to give to the human. So the human's model becomes gets to a point where they can correctly evaluate the plan risk, right? But that implicitly assumes that we know the human's model. And in many cases, this is not readily available. There are situations where this might be available, but this need not always be true. So the first question is, how do we relax this assumption? The first relaxation we'll consider is one where instead of having a single model, we'll have a set of possible models, and we just know that the human's model is one of these sets. So can we still generate explanations in this setting? And we also want to generate, in some sense, at least what would be considered minimal for this setting. And one of the possibilities here, so just to kind of give a little bit more background. So one of the cases where these kind of sets of models could happen is when you have annotated or incomplete models of this form. So what this basically description is saying is you have a model description where certain parts of the model is known, but others might be possible. So what this description, so this is a model description taken from this language called annotated PhD. And what it basically says that is, for the action pickup, I know that there's a precondition hand empty and not table. What I don't know is there might be a precondition that the block has to be light or not. So this is a possible thing. And when there is one possible annotation here, it actually corresponds to two possible models. One where the precondition is there and one where it's not. So as you can imagine, these kind of annotations can lead to like an exponential blow up within the model. The possible set of models. Okay, so the first set of possible explanation we can generate is what's usually referred to as conformal explanation. So under this scheme, for a given set of possible models, what we'll try to do is we'll try to find a single set of explanation that would work for all the models, right? And what that means is no matter which of these models the human's actual model might be, the explanation still works. And the way we will do this is basically by turning the explanation search into a search over belief space. So now you have set of possible models at each search node. And when you apply an action, it modifies all possible models in the belief space. We are trying to find out a specific node where all the remaining models actually would evaluate the plan. So one of the good things is if the original model set was represented using annotated PTL, we can actually leverage the structure of such representation to speed up the process. In fact, you can show that you only need to consider these two like possibly the most relaxed and most constrained model and do research. And you don't have to consider every possible model left in each belief space when you're evaluating whether that model satisfies the conditions that you are looking for in the goal evaluation step. Okay, so the second strategy is instead of conforming one, you can have a case where the robot actually creates contingent explanation. These are explanations where there are sensing actions in the form of questions. So the robot can ask questions to human. Should I do this? Not should I do this, but rather, do you know about this fact? Do you know about this precondition? And based on their answers, the system can provide different kinds of explanations. So this is another strategy you can use. You can also have like more of like an online version of the algorithm where the system basically makes optimistic assumptions about the human model, comes up with an explanation, tries out the explanation, and then repeats. So that's also a much more faster, but like a method where you can provide less guarantees. Okay, so the evaluation, I won't go into details here. Again, you can see the IPC models. And we didn't do a different user study because in the end, these are still, again, model reconciliation explanations. So in terms of the next possibility, one thing we could have is we could have cases where so in the previous section, we were still talking about cases where you have a set of possible models. So this could be a case where there are no such sets. You don't know anything about the human's mental model at all. But what is available is you can possibly collect data from people who have similar backgrounds. So you can kind of interact and collect information about how different explanations might affect how they view the plan. So one of the basic intuitions to use that we leverage here is the fact that in the end, all explanatory messages are coming from the robots. So you could have generated the set of all possible messages even if you did not know the human cycle. But why you need the human cycle model is to generate the most, in some sense, the minimal sets, the more effective sets, because you want to avoid redundant information. You want to utilize their prior views to get more effective explanations. So that's what we see. And we can kind of get away with it, even if we don't know the humans, the actual human model, by learning labeling models of this form. So where you have some behavior traits. So this particular work actually looked at a model reconciliation that conducted MDPs, and we were looking at specifically state action state traces, and we were looking at, given a state action state trace and given some explanatory messages, would the person say yes or no? So we collect a data set of this form and try to learn classifiers of this form. And once we have a classifier or a labeling model of this form, you can go back to your model reconciliation search and search over the set of actual explanatory messages. So each of the search nodes here corresponds to a set of messages, which in fact corresponds to a possibly updated method. Because when you're giving these messages, you're updating the model. So I forgot to mention, all the explanatory messages here are information about the robots. So giving a set of explanatory messages corresponds to updating their method. And you're basically going to search till you find a model where the behavior in question that you're trying to explain is going to be labeled by the learned labeling model, that it's actually going to be explicable. As in, like, for every behavior, the labeling model will say, okay, this seems to be explicable or not. So we will use that as a proxy to generate the explanation. Okay. So one of the things we did was we tried to see how well we can learn these kind of labeling models for like different settings, and we did both simulator study and user studies where we collected data from people over mechanical term based on they will give different behaviors and different explanatory messages, and we will try to see how their labels change based on the messages given to them. So, and then we tried different kinds of classifiers based on. So that brings us to the end of the first part of the talk. Now we'll go to the second part, which is focused on the question of how do we generate explanations when we have differences in inferential capabilities. So this corresponds to cases where, like this, just as a like, if you were to imagine this case, let's imagine a case where the human knew the model exactly that the robot has. So the MRH is the same as MR. But you could still have a mismatch in expectation if the human's inferential capabilities differ from the robot's actual capabilities. So even if they knew everything, the human might not be capable of coming up with or figuring out that this is the right course of action to be done in this situation. So in the course of my work, and specifically the ones that are provided in the dissertation and will be discussed here, I generally try to address this problem by looking at three possible strategies. One is to allow people to have more interaction with the system, specifically in the forms of foils, where the human can ask more pointed questions. They can bring out the question of, here are the different alternatives they were expecting, and use that to kind of drive the explanation process. The second thing is, instead of talking about or exposing the human to the true robot model, we can expose to simplified representation of the robot model. And that will, in some sense, reduce the inferential burden. The third one is what we call explanatory weaknesses. This is in addition to the model information we provide. You can give other information that demonstrate why some property that you're trying to explain for. So this, in my cases, most of the time, this corresponds to things like providing some example trace. So you are trying to explain why this policy might cause something, and you can walk them through like some particular trace of a policy and so on. And these are necessarily independent strategies. After all, the kind of model simplification that you can use and the effectiveness of model simplification might depend on the kind of questions you ask. So these are related strategies, and the effectiveness of one might depend on the others. So starting with the first one, I talked about letting the humans ask more specific questions, and I talked about this idea of foil. So this is the, we also saw this explicit contrastive form of the questions, where there's a plan that's being explained, and there are these alternate plans that the human were expecting. So in this form, in this case, we will allow the human to specify those alternatives. So they'll say, okay, instead of this, why did you not choose these other explanations, the other plans? Okay, so just as an example, you have this rover domain, and the human is asking, okay, why did the rover not go through this rocky road? Right? It seems much shorter. Why not take that road? So one of the explanatory framework I helped develop to answer those kind of questions was what's called as hierarchical expertise level modeling framework, or Helm framework, where what we do is we take this original true task model of the robot, create state abstractions, specifically abstractions where you project out some subset of state points. So we'll get a simpler description and use those descriptions to provide explanation. So generally the explanation itself takes this form of a search, where we have this lattice of possible abstraction. So each model in this lattice is projecting out some subset of points, and we are trying to figure out what is the most abstract model where we can still explain the infeasibility of the foil they had. The foil they were asking was, why not this plan, right? So if we focus on this model, we can see that, okay, the foil in question is still going to be invalid, and it contains much less detail than any of the other models. So we can use these abstractions to simplify it. It was also shown that you can kind of think about it as being a special case of model differentiation, but one where we are also thinking about simplifying the model in some sense. Yeah, so that was the basic Helm system. So you could also have cases where these kind of abstraction lattices could also be encoded to encode some specific domain level like intuitions the system might have about what might be easier or what might be harder. So this was an application of Helm within the context of task and motion planning. And what we did with the lattice here was we made sure that all the task level information are going to be at the top of the lattice. So the search for Helm always starts with the most abstract and then searches towards more concrete. And we'll always try to explain with just task level things if it's possible. But then you could have experts, right? You could have, this is a naive foil where the whole invalidity of the foil could have explained that task level information, but you could have experts, might be like robotics expert, who might ask more directed questions, which actually might require going at the level of actual like collisions and trajectories and so on. So then you can just kind of go at that level. So this video also shows an example of an like explanatory weakness. You saw like a simulation of how the collision would look like, things like that. So these kind of, in these Helm, we can also use these abstractions at different level to also show explanatory weaknesses at like different levels of details. Okay, so we still had the evaluation over IPC domain. One interesting thing I just wanted to note was you can actually map this explanation generation problem in this setting to weighted set covering. And one of the good things is weighted set covering actually has very good guarantees when it comes to greedy algorithms. And you can actually, we actually see that greedy algorithms actually work pretty well in regards to generating explanations. There is no optimal guarantee there, but you can guarantee upper bounds on how bad it can be. So the other thing we did was we did a user study where we looked at abstract explanations, the way Helm would generate, versus more detailed concrete explanation. And what we had here was basically we had a person playing a game. And here the different plans correspond to different like actions that a player might take. And the system would provide explanation at different levels of abstraction. And what we did was, what we were interested in seeing was, does these abstractions help reduce the cognitive burden on the user? And we use this famous score from human factors called NASA TLX score. And we actually see that use of abstraction does lead to less cognitive burden as measured by NASA TLX. And here are the different dimensions for NASA TLX score. You can actually see that the mental demand is actually reduced from 2.9 to 1.4 when we use abstract explanations. Okay, so that's the basic Helm framework. But since the introduction of the basic one, we've looked at various extensions. I don't think we'll have the time to go over every one, but one specific one that might be worth bringing up is this question of, okay, so when we talked about the framework earlier, we were talking about plans. So most of the time, it's very hard to expect human to give fully specified plans as points. A more likely case would be that a human might only specify a partial specification of what they were expecting. It's more likely that they would say, okay, why did you do this action? Or why don't you try this action? Instead of providing fully specified plans. You could also have things like domain control knowledge, like basically fragments of plans, right? Programs, right? Things like, okay, keep scrubbing till the dish is clean. Basically a loop, right? You're just scrubbing till it's clean. So these are all, regardless of the actual representation these information takes, what these partial files correspond to are constraints over the initial planning problem. And what the user is asking is, I would like to see, would like to understand why you haven't selected a plan that satisfies these constraints. So basically, explaining why I cannot satisfy a constraint corresponds to basically explaining why this constraint planning problem is unsolvable, right? Why there are no valid solutions. Which effectively means we need a way of explaining unsolvability of planning problems. So we can again use the same strategies that we looked at previously in the case of explaining individual files, but now we are looking for abstract models where the whole planning problem might be unsolved. So, in fact, the original planning problem I presented was unsolvable, but it's the form takes the same, like the way we generate explanation takes the same form. You have a search over this abstraction address, but while you're looking for an abstract model where the problem is unsolvable. And one of the additional things we added here was that when we're talking about unsolvability, one of the things we can do is rather than talking about the entire planning horizon, the original planning horizon, we can decompose the planning problem into smaller problems. We can talk about subgoals. So if you are talking about why this rover cannot reach the green cell, we can instead talk about, okay, the rover cannot even reach this red cell, let alone the green cell. So we decompose the problem into smaller problem and talk about, and just focus on that smaller problem so the human doesn't have to consider the whole price. And we actually use planning landmarks to do these kind of decomposition. I won't go into details too much, but one of the interesting things is if the problem is unsolvable, you won't even have one. So one of the technical challenges here was how do we relax the planning problem so we could have possible plans, then possible subgoals, and then use those kind of subgoals to come up with the simplified model. So I've also looked at extensions of Helm beyond classical planning. In fact, we looked at the application of such methods in the context of non-deterministic planning model. Again, given the time, I won't spend too much time on this, but this was actually implemented in the context of a domain debugging tool, where you had for a specific application, you had people who were specifying non-deterministic domain models, and they wanted to debug why the behavior they were seeing was not what they were expecting. And one of the things we had was, we also introduced in that work, we had used almost all the techniques we talked earlier in that thing. And we also, and this was all done within the context of non-deterministic planning problems. And one of the additional things we did was we introduced this new kind of explanatory weakness where we will show a failure of, so in the context of unsolvability, we'll show some example plan traces and show how it might fail. So one of the things we did was we took, one of the problems with generating these kinds of possible explanatory traces is the fact that if you were to try to relax it even further, because we are trying to talk about these traces in abstract model. So if you relax it further, most of the time the traces might actually be very uninformative. It might be just saying, okay, if you did one action, you'll get the goal, things like that. So in fact, one of the challenges here was we were looking at more concrete models from where we can generate the trace and show its failures in the more abstract model. So you'll get a little more informative trace information, at least failure information in those cases. So one of the things we can kind of do here is, in fact, in the previous section, we looked at two ways of simplifying the mod. One was state abstraction, where we were projecting out certain state lines. Then we looked at how we can take the original planning problem and decompose it into sub-problems corresponding to subgoals. But we can take this point one step further. There are other ways of simplifying the model that goes beyond this abstraction and subgoals. Even from the planning literature, some of the examples include things like local approximation. So you find a representation that's only valid for some subset of the transition system. So not consider the entire problem, this is a subset. You can do determinization. So when you're talking about, maybe the original problem was stochastic, but explanation doesn't really, the explanation doesn't really have to touch about the stochasticity of the system. You can just talk in terms of a determinized version of the problem. And you can also, in some cases, as we saw, we can remove motion level constraints and still provide a feasible explanation. We can sometimes remove numeric temporal constraints and still provide a feasible explanation. So these are all different kinds of model simplification that we can apply in the context of explanation. And one way of kind of generalizing everything we talked about is to think about this process where each explanatory query correspond to this problem of establishing a property that you're trying to explain. So there's some model property you're trying to explain, saying that the best plan that could have come out of this model cannot cost less than X, or the probability of the. So this particular work, this is a new work that's discussed in the dissertation, was done in the context of MDP. So there is, and particularly max prob MDP. So you had policies which were not guaranteed to get to the plan with probability 1. It could have probability less than 1. So you could have questions like, okay, why does this policy not lead me to goal with probability greater than some point, something like that. So here, in each of these cases, you're trying to establish some property of the model. And what we can do is, given our set of transformation, we can take this original model, look at what's the most simplest model we can form by applying this transformation, where the property still fits. And we can use that as the basis for explanation. But the thing is, what does it mean to have a simpler model? Right? Here, really, to have a simpler model, to see whether or not a transformation makes a model simpler, you need to have a model of human cognitive abilities. And unfortunately, we don't quite have that right now, or at least I haven't seen works that are able to do it. So do it like with guarantee. So one of the things we can do is use computation proxies. And some of the proxies I've looked at within that chapter is things like, okay, the size of the description, or the time taken to establish the property in that model by a complete or sound reason. So we use some kind of a, like a oracle kind of reason, not oracle, but just like a more a computational reasoner to see how much time that reasoner takes, and use that as a like a lower bound of what human might take. So the dissertation of that chapter also includes results on some of the user studies that were done to evaluate different kinds of transformation and whether people are more accepting of one form of transformation as opposed to another. Yeah, and also I looked at I specifically looked at transformations that generate optimistic approximations of the model. So you'll never get a case where one of the transformation will result in a model which might. So I'm trying to explain why the cost of my policy is high, and you'll never get a model where there is a policy with higher probability than what I can, or like lower probability than what I can. So here we are always the good thing with generating optimistic approximations is the human would always want to ask more questions. You never stop the human from asking more questions. So that's the kind of transformations we focused on in that chapter. Okay, so in terms of the third dimension, we'll talk about like vocabulary mismatch. So through all the previous chapters, previous parts, we talked about cases where the robot was giving information about the model or giving some explanation. All of these works makes the underlying assumption that the robot can actually effectively communicate with the human some information about itself. And that means that both the human and the robot share some vocabulary as a starting point. And this need not be true, right? Especially in cases where the agent might be using some kind of learned black box model. How the robot is representing the state might make zero sense to how the human is viewing the task and how the human might be understanding the task. So in this particular part, what I looked at the possibility of generating post hoc symbolic models which are expressed in users' vocabulary, which can then be used as a basis for explanations. So the basic form, at least in my primary work in this section, what I looked at a case where the human gives a set of concepts in terms of these are binary concepts that correspond to some possible proposition influence in the world, and the human would give some positive and negative example. And you build a classifier out of it, and then use it as a basis to learn some model component that can then be used to provide explanation. So specifically, we won't learn the full model. We'll in fact learn parts of the model. And the two parts we were interested in was looking at learning preconditions and abstract versions of the cost function. So we were specifically, because we were trying to model things like Montezuma events. There are a lot of conditional effects and conditional costs in these kind of settings. So we were looking at conditional cost functions, and we were trying to learn abstract versions of it to use some subsets of the plan rather than giving you like a full cost function. So basically, the algorithm we had was a sampling-based one, which would interact with the simulator to generate some experience, some sample experiences, and then use these classifiers to build some an approximate version of the symbolic model, which can then be used for explanations. One of the challenges with using such post-hoc explanation, that is explanations where you're coming up with the reason after the fact, is the reason that you give might not have anything to do with why you came up with the decision in the first place. So we try to avoid that problem, at least to some degree, by providing these kind of confidences over explanation. In this specific case, we were trying to generate a probability of, right, when we are using sampling-based methods, we are using noisy classifiers, how likely is that the precondition you found is actually going to be a precondition? Or if only you had sampled a little bit more, maybe you would have found this was not a precondition or something like that. So we generate some kind of probabilistic confidence on these kind of model components that you learn. So again, we did human studies to validate the explanation. We did some subjective study on whether people actually like this kind of explanation over ones that just replay the foil and show where it fails. Do they really care about giving like these kind of concept explanation? And the other interesting thing we did was we compared it to saliency map-based explanation. And this was an objective evaluation where you had a player who was supposed to play the game, and they were either given concept-based explanation or saliency-based explanation. And as you can see, when you have concept-based explanation, they are much more, on average, they took much less time to complete the game, much less number of steps to complete the game. So in some sense, they were able to understand the task much better when they were given concept-based rather than saliency-based explanation. Okay, so the next three sections, given the limited time, I won't spend too much time in all of the sections, but one of the things I kind of wanted to talk about was the fact that at the very beginning, I said there were two kinds of ways of addressing this problem of inexplicability. One was generating explanations, the other was explainable planning. It wasn't totally true because there is this middle way where you can kind of combine it. What it basically corresponds to is, instead of choosing the robot's optimal plan, you can actually choose to do a plan that might be a little bit more suboptimal, but easier to explain. So what this video shows is the optimal route that the robot has actually requires a lot of explanation. It has to say that, okay, there are multiple places which are free and things like that. But this slightly more harder path is actually easier to explain. So you only need to give one model update, and then the human would think this is the right information. So in some sense, what we get is we have a new planning formalism where the objectives of the planning doesn't just include the cost of the plan, but you also have to talk about the cost of communicating some explanation and potential penalties from doing something that's inexplicable or unexpected to the human. So you'll get a new planning formalism. And we call it expectation-aware planning. And one of my contributions was presenting a classical planning formulation that's built on earlier works on epistemic planning that allows you to represent these kind of explanations. So I won't go through the compilation, but one of the interesting things here was that now the state of this compiled model doesn't just include the state of the planning problem, but includes what the human believes the state would be. And also the state includes what the humans believe about the model is fair. And in these kind of settings, explanations itself were mapped into just a set of actions with epistemic effects. And what that means is you can now come up with a single plan that includes both explanations and the actual steps it has to do with the plan. And this has the other advantages, like you can now capture epistemic side effects of robots' actions in the world. So if the robot does something, the human might understand things like, okay, if the robot tries to wiggle a door handle, it kind of knows, okay, the human might be able to say, actually that door might be locked. So that's like an epistemic side effect of a robot's object action. You could have the opposite aspect, right? There could be things like robot explaining something or communicating something might reduce the battery. So it might affect what the robot can later do. So these kind of, this combined representation allows you to capture those things. And you also get advantages in terms of actually coming up with the explanation, because now you can use planning heuristics and things like that. And also these kind of balancing communication and interpretable behavior generation goes beyond just explicability. You can also have, you can also balance predictability, like that is, you can communicate so that the robot's behavior is easier for the human to predict. You could communicate to reduce uncertainty the human might have on the robot's model and so on. As a first step towards allowing these kind of balancing thing, one of the other things I've done was introduce this, what we've been calling generalized human-aware planning, where we have a single planning formulation where we model the human as a Bayesian reasoner over a set of possible models. And based on the kind of reward function we specified for the planning problem, all the different kinds of interpretability measures that has been studied in the literature, whether it's explicability, legibility, or predictability, this falls naturally out of it. So by providing the reward function that focuses on, let's say, ensuring that the human's predictions about the robot behavior aligns with the robot's plan, it automatically will generate predictability behavior and so on. So here the compilation is actually, the formulation is kind of similar to what you had earlier, because now the planning state not only includes the robot's planning state, but also includes humans' beliefs about what the robot model or the robot state can be. And the transition function here includes how robots' action will change that. So this is, we have like a Bayesian formalization for that kind of captures all the existing interpretability measures under the Asymmetry umbrella. Yeah, this is just like showing how the same formulation allows you to support all of the formulations. And now to kind of talk about this problem of communicating decisions. In all the previous sections, we talked about how to explain decisions that the robot came up with. But there is a part that I skipped. For example, how does the robot actually communicate what it's going to do to the human? This can be especially hard in stochastic setting where the solution concept corresponds to things like policies. So policies has to take into account various contingencies, and it might be very hard to just give that directly to the human. So one of the things I looked at was, I considered, so this is just as a simple example. This is like a very simple domain called exporting blocks. And this is what the policy looks like for that. So think about just keeping something like this to the user, right? So you don't want to do that. You want to simplify it. So you can give it in a form that's easier for them to understand. And so they can expand and like drill in as required. So this is the summary for that policy that you saw. Basically, what the summary consists of are the various sub-goals that needs to be achieved by that policy to get to the goal. So you can kind of, what you've done is we've taken the entire policy and broken it up into the various sub-goals. And now, as required, the human can like, focus on one specific sub-goal and then see what exactly, which the part of the policy that corresponds to achieving that sub-goal. So you can now use it to focus on different parts of the policy. Okay, so we are nearing the end of the talk. Before I do it, I just also wanted to say that beyond just as a way of categorizing my work, this human-aware explanation, the dimensions can also be thought of as a way of understanding the different works which has been done within XRP that goes beyond just like what I've done. And I just wanted to quickly flash a summary of some of the things. So here I've listed the 3 dimensions and like from the works that I looked at within the Excited community. Here are like the different works, the number of works that try to address these different dimensions. In particular, for knowledge asymmetry, I just looked at works that are guaranteed to reconcile different, like all the required differences. But there are, in fact, there are a lot of works within the literature that actually, in some ways, exposes model differences. So there can make assumptions where that will be enough. But for this slide, I just focus on that part. More details are in the dissertation, and I can also be happy to talk about more in the question and answer session. Okay, so to end as the last part, I just wanted to talk about where could we go from here. So through this talk, I mostly focus on cases where we were only thinking about one direction of communication. The robot was trying to explain to human, but for effective collaboration, we also have to go the other way. The human has to be able to provide information to the robot in some ways. Things like it might be want to provide preferences, instructions, demonstrations, and so on. So I want to make the case that in this when we are looking at the human providing information to the robot, one way to understand it is what the human is effectively trying to do is they are taking MRH, what they believe is the robot's current model, and trying to update MRH. Because this is what they believe the robot's model is. They have some agenda of their own. So they're trying to update it, and they're going to give information which they believe will update it to a model where they get the output or behavior they require. So you can kind of see the symmetry here, right? You have the robot updating MRH before. Here you have the human trying to giving information, trying to update MR while having MRH, while using MRH as the basis of coming up with the information. And all the three dimensions we talked about are still going to be relevant here, because when they give some information, right, and there is some difference between what the robot and the human knows, that is going to color what information that will be given to the robot. So all the things that we discussed here are still valid and needs to be investigated in these kind of settings as well. And there are additional challenges like, okay, how do we convert human instruction to machine usable one? How do we indent human intention behind input? They may say something, but they might have something else in mind. And so when the robot is trying to make sense of it, it might have to use the current MRs to figure out what the human actually meant. And also there is the question of how do we come up with an effective interaction? And that kind of ends the technical section of my talk. So I just wanted to quickly flash the fact that I've been lucky enough that my work has had some significant impact in the community, and I've had chances to help the community in a few ways and also present my work at different venues. And that brings us to an end of the talk. So within this talk, we looked at different challenges related to explanation generation for sequential decision-making problem. And we looked at the various works I've done to address those challenges. Especially, we looked at it in this context of understanding them along these three dimensions. And that's it. I'll be happy to take any questions. Thank you. Oh. Yeah.
Thank you for your presentation. So right now the floor is open for questions from anybody, including the audience and committee members. And then there will be, after this, there will be a closed session where committee members can ask more detailed questions. So yeah, if any of you have any questions, either on Zoom or here, please feel free to ask. Sure.
Oh, I think you may have to raise your hand first. Yes.
So you spoke about the explanatory witness,
yeah,
one of the approaches where you give a trace of, say, why you plan. What are the challenges or issues with this method? Like,
so just to specify something, explanatory witness, I usually use it in a more general sense. In fact, in the dissertation, I go over the kind of different types of explanatory witness as have been looked at in the literature. Looking at sample traces is just one of them. There are other ones, right? So just with sample traces, things like, so you just wanted to know what are the challenges specifically related to generating sample traces or like in general? Let's start with the traces. So one of the things is still the question of, we're talking about a 1,000-step plan. Right? You don't want to walk them through 1,000 steps of execution, right? And there is still the question of finding abstract versions, which is still already there. You want to present this information at an abstract level. Then there was the other challenge I kind of talked about, where when you're talking about unsolvable, right? One of the problems is there is no traces to talk about. So the thing is, what you don't want to do is, yeah, I can't do it. Right? Like, but how do you trust that I can do it? I will come up with traces which you might think are easy and say, okay, this is how I assume it. So that's like a challenge in itself. When you are asking, if you had some kind of foil, that is much easier because I know what to expect and I'll walk you through the foil. But still the question of how do I summarize the foil, how do I summarize the errors and stuff like that. But in general, the question of how do we generate this information. Yeah.
So one follow-up. For the sample traces, don't we implicitly have to consider any epistemic effects of that?
It depends. So the point is right now, in the kind of settings I looked at, I was giving the model upfront. So I was giving an abstract model upfront and then walking you through it. So it kind of already includes. Yeah. So, but in the most general sense, if I was like looking at the model reconciliation case where I'm only some parts of it, I'll have to account for it. Yeah.
Thank you.
Yes.
Yeah, so when you were talking about providing unreasonable subgoals,
yeah,
you had this example where the user tried to go to this red dot at the and you were explaining about like it wanted to go to a green dot. I think it's slide 63.
Okay. Yeah, but go ahead.
Yeah, so in that you are assuming that the user understands that this is that it's a subgoal that it has to reach, right?
Mm-hmm. Yeah.
Otherwise, the user would be like, "Hey, I wanted to go to green. Why are you explaining about the red zone?"
Right. No. So the point is, the way you would present it is that, like, if I need to get to red block, I have to first get to this. Right. So you would say, okay, let's assume that you don't believe it. You assume that you actually don't have to go through that red block to get to it. Then you would give some other foil, right? Okay. Use that. Then you have a different foil. The interaction continues. So it becomes like an interactive process. Right. Yeah.
Other questions?
If nobody's asking, I'm just curious what. So in that help video that you showed, right? I think it was around slide 55. So you were talking about that an expert can give a foil versus some.
Yeah, I think it's 56.
Video.
Yeah.
Yeah. Yeah. So the foil that comes, it has to be in terms of the concept that the model is represented in, right?
Yes. So here, sorry, please finish. Yeah.
Yeah. So I cannot actually ask questions like about the collisions that were there because that may not be part of the model, right?
So we are not talking about collisions here quite. So the foil here was still in terms of, okay, do the sequence of actions. So the first foil was basically, sorry, I've been kind of like flashing through that, so it's kind of hard to follow. The first question was, okay, the human is asking, why don't you place the judge? This was the naive, right? So it's fine. The other one was, if we skip it a little bit, the foil was basically saying, pick up the judge in lower grasp. Yeah, but so at this point, we are assuming that the person who's asking has a concept called lower grasp. So that's the assumption. So we are not quite handling vocabulary mismatch here. So just people with different levels of vocabulary, it is just corresponding to different abstractions. We are asking this. So we'll go down to that abstraction and try to explain.
I have a question on a very different aspect. I mean, you basically touched on it, that complexity of explanation generation is
And model.
Yeah, model. then you had a model. The kind of models changed.
Yeah.
Have you? Wondered how the complexity changes for those higher levels?
I haven't considered other problem formulations. Yeah. But just to, at least the Helm one is in. And also the balancing is piece-based company because it's a planning aspect. But I haven't looked at NDPs, conformant ones, those ones I have.
No, I was actually interested in the Helm part.
Okay.
I thought more information.
Yeah, the Helm one actually corresponds to the same the weighted set covering problem, which is an anti-complete.
Other questions, especially by audience? Of course, committee members can ask anytime.
Okay.
It's 110 outside.
Yeah. Thanks for reminding me.
To slide 40.
40. Yes.
So the possibilities you're considering here are initial case in which you know what the user's problem is.
Yes.
And then in the second case, it's using you know nothing. Big middle ground here, right? So students have some physics, right? Have knowledge that they know some area, but you'd be less certain about their knowledge about periphery and surroundings. And so I'm wondering how you count some,
So just to correct it, it's I'm sorry that because I was just rushing through things. The second one actually corresponds to what you were saying, in that this was the middle ground, which is basically you have a set of possible models. So the way I generally view it is in terms of this annotated model, where there are parts of the model that you know for sure that the human knows, and then there are parts that you're uncertain about. Would that be
right? I'm not comfortable here with suggesting that one could characterize what you know and don't know about users in terms of missing precondition, missing facts. It's sort of more, they may be totally missing actually knowledge, vocabulary.
Okay.
Right.
Okay.
Some part of it, but
so again, so there is what can be represented versus is the most effective way of representing it. I would still say that in the end we could represent missing action as yet another action where all the preconditions are possible, all the effects are possible, right? Initial state changes are effects, possible effects. Then there are vocabulary mismatches. Every place that vocabulary could be possible. Every action has a possible precondition. But I agree that might, in some sense, even though I want to argue that that representation is complete in the sense that it can represent it, but I agree that it might not be the most effective way of representing it, right? Okay, so that's one. The second thing is, let's assume what happens when you don't want to capture that information, right? So let's assume we start with a human mental model where we start with only the things that we know, right? And the rest we assume it's not there. Let's for now assume that's the right way to represent it, right? So it's not there. Now the question is, how do we kind of generate explanations of that form? So one of the things there you can still do is, so here, one of the questions I have is,
are we looking for an interactive form of this kind of teaching where we are going to query them for, do they know this information or not? Or do you more looking for like, okay, regardless of whether they know it or not, I'm going to come up with some explanation that will cover their basis. Which one would you feel? Because I think I've done both kind of works. So if the
my intuition here is that you make some assumptions about general explanation.
So one thing you can do is, in fact, one of the models you can use for that process is the Helm kind of system, where you have this abstraction lattice where where these different parts of the abstraction correspond to different kind of knowledge sets, right? So there are certain cases where the human might not know. And based on the kind of question they ask, you could try to place them, which part of this lattice they might lie in. Then use that as a starting point to ask the question. So that's one way I would imagine we could do this kind of explanatory process.
All right, my next question is about
Okay.
Yeah. So, screen. In one case, you may give drop this thing that gets around in 10 seconds.
Yeah.
Okay. And it doesn't understand.
Right.
And that's where you're actually talking about Mars. So,
right.
So that's a simple case where there's just a constant there.
Right.
Right.
Okay.
So it's linear rather than very
right.
entirely.
Yeah.
So you want
Yes.
what you can do about that.
It's just to go back to the model simplification thing. So the one place where I did use numbers, where actually this newer work where we were talking about model simplification, we had probabilities. And one of the things I found out, at least, again, it depends a little bit on the end user, right? So I'm running user studies and probably people who are not experts. But even the user study, I did make sure that they at least declare themselves to be knowledgeable for probabilities, but who knows what that means. But at least one of the things I found out, and this is also supported by social science and like different people from other fields, that they said that people generally don't like numbers, and they are, especially with probability, they are really poor probabilistic reasoners. So even when we are talking about probabilities, even we are talking about temporal constraints, we are numeric constraints, there could be scenarios where you can still explain something by like kind of abstracting. And that's been one of the things that I've looked at. And even in the case of things like, okay, why is this policy costing me greater than this? You're talking really about expected value. But in their case, let's say we assume the cost was, the question is, I want to get a policy that whose expected value is less than 100. That's it. That's the thing. So you can still go to a determinist level and say, the shortest route I can take in this determinist value is still going to take more than 100. So there you've taken a probabilistic thing and kind of reduced it to like more deterministic, discrete kind of setting, or a deterministic discrete setting. But I agree that there might be cases where you can't get at the end. You have to refer to the probabilities. You have to refer to the numerical constraint to explain these things. But the framework itself stays the same, right? You can still talk about, I'm going to use this kind of an abstraction. I can still try to project out other variables. Right? The specific techniques might depend on the situation.
I believe that
So it depends.
Actually, because of the time constraints of the committee members, I probably, unless there are additional open questions from outside, we would like to end the public session and sort of continue doing this discussion, session, because I think one of the committee members has some constraints.
I'll just stop the recording.
Yeah.